So what we're going to do today is we're going to do more with recurrence relations. We're going to do generating functions. This is one of the most important concepts in mathematics. So I am teaching 3 different 300-level classes. It is very hard to keep them straight. It's very hard to remember which one of you is in which class. What have I done in which class? I have come up with a solution. And it's an efficient solution which goes well with my linear programming class. I'm just going to teach the same material 2 or 3 times a day. And then that way I don't have to really worry about have you seen it before, because you will have seen it. And I don't have to worry about preparing all these different things. So this will make life much easier. So for those of you who happen to be in multiple classes, it's somewhat deliberate. And if it gets too deliberate, let me know and I will work on it. So I made a comment in, I think, 389 today about series solutions to differential equations. And maybe I thought about making it. Or maybe that was in linear programming. They're all blending together at this point. But generating functions is similar to that. How many of you have taken differential equations? So one of the ways of solving a differential equation is you have this series solution with these undetermined coefficients an. And then you do some magic, you do some rearrangement of the series, and the coefficients pop out. And you can actually get a series solution for many problems. And the question becomes, does the series converge? What kind of properties does it have? Generating functions are going to be very similar to that. The algebra for the generating functions can become quite tedious. The idea is not so bad. So I thought before going into the generating functions and all that stuff, I thought we would start first with a problem and just do a nice recurrence. So the one I want to do is the following. So exercise. So let's let in be the integral from 0 to pi halves of the sine of x to the nth power dx. And so, not surprisingly, the goal is to find in. What should you do in a situation like this? How should we attack a problem like this? Try small cases. If you can program in Mathematica or some language, it's not so hard to do some small cases. So calculate small n. Do we think that there's going to be any difference if n is even or odd? Why could there be a difference if n is even or odd?
I mean, on a larger interval, you would worry about cancellation.
Right, so will we have any cancellation? So we're not going to have anything trivially 0, because we're going from 0 to pi halves. From 0 to pi halves, sine of x is always positive. So there's not going to be any difference in sign because of n being even or odd. But there is a huge advantage between either n even or n odd. One of them is much easier than the other. Anybody know which one is easier? Yes?
Even.
Even. Why?
Because you can use the trig identities to break it to lower the degree.
Good. Which trig identity do I use?
Sine squared x is equal to 1 minus.
Excellent. So if n is even, sine, actually I want n to be odd. Sine of x to the 2m plus 1 is 1 minus cosine squared of x to the m times sine of x. And so if I'm in this case, I can use your identity, and now I'll have cosine to an even power, and I have exactly what I want for the derivative. Can I handle the case of m even? Can I handle the case of n odd without too much trouble? Can I expand this out? Yeah, it's not going to be that bad. And so I would get, this would equal the sum, L goes from 0 to m, of m choose L. And then I'm going to have negative 1 to the L cosine x to the 2L times the sine of x. We integrate this from 0 to pi halves, and this would be I of 2m plus 1. Can I do the cosine integral? Yeah. The problem is, at the end of the day, will I be able to do anything with what I get? And so if I continue, I will have, I can replace it. Sum goes from 0 to m choose L, negative 1 to the L. When I integrate cosine, what do I get? I get sine, right? So I don't have to worry about any more negatives coming in. So I'll get sine of x to the 2l plus 1 over 2l plus 1. And now I evaluate this at 0 and pi halves. When I evaluated 0, I get 0. When I evaluated pi halves, I get 1. So I get the following expression. And so the question is, does this simplify in any nice way? Okay? But this is one way to attack the problem. This is one way to start the problem. How would you try to figure out if this simplifies? What could you do to try to see if this simplifies? Small examples. So when in doubt, small examples. Draw a picture. Okay, picture like that's not going to be that helpful, other than maybe trying to remind you that there's pleasant things outside this classroom. So we have something like this. Try a couple of values of m, see if you detect a pattern. Notice this is a lot easier to snip out the pattern here than maybe going back there into the original one. Unfortunately, this completely ignores what goes on for for even values of n. Okay? But it turns out that this is actually giving us an idea of how to attack. So the key idea, the suggestion was use trig to replace sine of x squared with 1 minus cosine squared. And that was really nice if we had things to an odd power. Because if we had things to an odd power, we then had one extra sign left over. What if we had things to an even power? What would have happened? Yes?
You wouldn't have had it left over and then actually do it.
We'd have to do integration by parts. So the question is, how could we try to attack this? So let's say we have in is the integral from 0 to pi halves of sine of x to the n dx. Let's try to find a recurrence for in. Because if we can find a recurrence for this, maybe we can use that to somehow solve the problem. All right, what can I assume about n? Well, if I assume it's even, then I would have to figure out a nice way to handle that. So I don't necessarily, it's not bad, but I don't want to assume n is even. What should I assume about n? Okay, n is an integer. What should I assume about n?
You assume it's large because the larger thing gets the
Yeah.
smaller it gets.
N is huge. N's like at least 2. I can handle n equals 0, n equals 1. I can handle these directly. If I want, I could even handle n equals 2. N equals 2 is not so bad. Let's assume n is large and try to sniff out a recurrence. Why do I want n to be at least 2? Well, I know I can replace the sine squared with the 1 minus cosine squared. So I would get in is the integral from 0 to pi halves. Now I would get 1 minus cosine squared of x times sine of x to the n minus 2 dx. All right, so this is in is the integral from 0 to pi halves of sine of x to the n minus 2 dx minus the integral from 0 to pi halves of cosine squared of x sine of x to the n minus 2 dx. All right, what can you say about the first term? It's the previous case. So far, so good. In is in minus 2. We're getting a recurrence relation. What about the second term? Is this a previous case? Your head's gone, I think, almost a whole 360 degrees. Is this a previous case? Is this I sub something? Okay, then what is the something? So our definition is, I sub L is the integral of sine to the L. We have a cosine squared.
So can you replace that with 1 minus sine squared?
Okay, so I could replace the cosine squared with 1 minus sine squared. The problem is if I do that, what's going to happen? I'm going to get back to where I started. Because I initially replaced the sine squared with the 1 minus cosine squared. So if I replace a cosine squared with the 1 minus sine squared, I return to where I started. I can't do that. How should I tackle this integral? What would make your life a lot easier if I changed something a little bit? What could I do to make your life easy? I'm sorry? What should I do? Change this ever so slightly, a really small change. What's a small change you could do that would make this integral really nice?
Maybe we're just like cosine instead of cosine squared.
Yeah. So just remove the 2. Can we do that? No, okay? We can't just remove the 2. All right. But let's think about it. If we didn't have that damn 2, if we just had cosine of x, life would be good. We would know how to do it. So let's look at it as sine of x to the n minus 2 times cosine of x. And we're going to block them off together. And then in the next block, we're going to put the damn pesky cosine of x. So if this factor hadn't been here, we would be fine. Why? This is the derivative of that. We could integrate this very easily, and we would go from a sine of x to the n minus 2 to a sine of x to the n minus 1 over n minus 1. Maybe with a plus or minus sign, I don't care. How should we handle this? Integration by parts. And so u should be, I'm sorry, I want this to be dv, because I've got exactly what I need here. So dv should be the sine of x to the n minus 2 cosine x dx. U should be cosine of x. Du, derivative of cosine, is minus sine of x. And v is going to be sine of x to the n minus 1 divided by n minus 1. And let's check. The derivative will be n minus 1 sine of x to the n minus 2. And the derivative of sine is cosine good, so I don't have any minus signs that I'm missing. And now when I have the boundary terms, I'm going to have uv at the boundary. When I put in 0, the sign will be 0 because n is at least 2. And then when I put in pi halves, that will be 0. So the boundary terms vanish. And we're left with in is in minus 2 minus the integral from 0 to pi halves. But when we integrate by parts, this minus becomes a plus, right? Because it's uv at the boundary minus the integral of v du. And now I'm going to have sine of x to the n minus 1 divided by n minus 1 times, so I'm going to have v du times sine of x. But that has a minus sign, so the minus sign now comes back. So it's a minus sign. We lost the minus sign because it's the negative integral of v du, but then the du had a minus sign. From a minus sign, actually. And so that came back. Yes? I'm sorry? Yes, it is. And so we get in minus 2 minus 1 over n minus 1 in. And so what we've now got is we now have, the camera doesn't seem to like to move. So we now have the recurrence relation that we've been looking for. And so now we have an in minus 2 minus in minus 1. So let me just write that over here a little bit nicer. So we'll throw away all this stuff. And what we've just shown is at least if n is greater than or equal to 2, in is in minus 2 minus 1 over n minus 1 in. So you might have seen something like this in calculus. I call this the bring it over method, when you have what you want on both sides. And now it's just algebra to solve. We bring this over, and we have in plus 1 over n minus 1. So I think we get n over n minus 1 in is in minus 2, which means in is n minus 1 over n times in minus 2. At this point, I will leave it to you as an exercise to figure out what the final answer is. What do you think the final answer is going to involve? You want to get to the point where you can sniff out answers. What function, what expressions do you think are going to occur in the final answer? What do you think is going to come into play here? Well, if you want, we'll do one more. In minus 2. So we replace n with n minus 2. We get n minus 3 over n minus 2, in minus 4. So this would also be the same as n minus 1 times n minus 3 over n minus 2 times n minus 4. What do you see the solutions involving now? Not choosing. What do these look like as we keep going down? N minus 1, n minus 3. They involve factorials. So this will be one parity down here, another parity down there. You're going to have strings of factorials. So you want to be able to get a sense of what the answer looks like. So I'd like you to try to play with the rest of this and see, can you come up with a clean formula for in from this? The other thing is, whenever you get an expression, whenever you get an answer, you want to check and see, is this reasonable? So I'm claiming in is n minus 1 over n minus 2. Does that seem reasonable to you? What does this mean? What is the consequence of this relation? The ions are getting a little bit smaller. Does it seem reasonable that as n gets larger, the ions get smaller? Yeah, we have a number that's between 0 and 1. The higher power we take it to, the smaller it gets. If n is really large, does it make much of a difference to go from raising this to the millionth to the million plus first? No. So this has a lot of really good properties. And again, this is far more useful than the actual solution to this problem. Being able to look at an answer and say, is this reasonable? Does it have the properties I would expect? I expect my solution to be non-negative because I'm integrating something that's non-negative. I expect it to get smaller as n gets larger. I'm seeing that. When n is enormous, I don't expect there to be much of a change. What else might you expect as n gets very, very large? It goes to 0. That's a little bit harder to see here. It's being multiplied by the factors 1 minus 1 over n. If you've seen the Riemann zeta function or various other things, you can probably convince yourself that this will be going to 0. But that's another thing you should expect to see for something like this. If you think about this, the function is going up to 1 only as we get very, very close to pi halves. As we stay away from pi halves, this function is going to be a number less than 1 raised to an enormous power. It's going to become insignificant. So you want to be able to get a sense of the solution before you actually roll up your sleeves and do the calculation. So at the end of the day, you get, is this reasonable? Okay. Any questions about this problem? Okay. So what I want to do now is I want to turn and I want to do generating functions. So the algebra is going to be a little bit involved here. By all means, if you want to just sit back and just try to keep your eyes open, that's fine. You don't need to write this down. This is in the handouts that I've posted online. This is just the standard proof for the Fibonacci numbers. If you have seen this before, I apologize, but it's such a great result, it is worth seeing again. To me, this is one of the most magical things you can see in mathematics. You start with the Fibonacci numbers, and you start with them in the following form. We know f of 0 is 0. We know f of 1 is 1. We know f of n plus 1 is f of n plus f of n minus 1. And I'm going to write down this new function, g of x is the sum, and it goes from 0 to infinity of fn x to the n. So if I'm going to write down a power series, if I'm going to write down a function, it would be useful to know the coefficients of the function. Right? If you had a wish list of things you would like, if I'm writing down a power series, if I'm writing down a series expansion, I'd like to know what the coefficients are. Not knowing the coefficients is a bit of a problem. I want to work with this function g of x. Do I know the coefficients of g of x? Okay, so you're shaking your head yes. Why do I know the coefficients? Or what are the Fibonacci numbers? Does that tell me what the Fibonacci numbers are? We don't know that. We don't know Benet's formula. We were not divinely inspired. We did a little bit too much, over the weekend and just kind of groggy right now. God has turned his or her back on us. We are on our own. We do not know what the answer is. It's sad. But we write this down. Do we know the Fibonacci numbers?
No.
Do we know the 0th Fibonacci number?
Yes.
The first Fibonacci number? The second?
No.
Yes. Right? We know the 0th and the first. We can calculate the second. So the question is, what do we know? We haven't codified it. We haven't written it down yet. If we needed to write it down, could we? Yes. Could we write down the next one? And then, yeah, we can write them. Once I give you this information, everything is determined. It's just not necessarily determined in a useful way. If I want to jump to the 1000th Fibonacci number, I have to go through every single Fibonacci number beforehand. But it's all there. So the question is, can I somehow get something useful? It is not a coincidence that before doing this, I wanted to do the integral of sine of n. There's a lot of similarities between these two problems. This is foreshadowing. It's entirely coincidental that this was being done at 3 in the morning, because coincidence, right? What is similar between that and what we're going to do here? What was the key idea that allowed us to solve for in just a few moments ago? I'm sorry?
Too big. I stopped it.
Okay. Why were we able to solve for i's? We could relate them to previous cases. So we got in was equal to in minus 1 plus some constant times in again. And that constant was not 1. We could bring it over, and then we could express in terms of other stuff. We're going to do the same idea here. We're going to use this bring it over method again. This is one of the most important ideas in mathematics. We're going to solve for g of x by getting a nice expression multiple ways. Well, the only thing we know about the Fibonacci numbers is fn plus 1 is fn plus fn minus 1. All right, so let's start off. So we have g of x is f of 0 plus the sum, and goes from, I'll do it this way, f of 0 plus f1 of x plus the sum, and goes from 2 to infinity of fn x to the n. There's a lot of ways to do the algebra. I really don't care which way you do the algebra. I'm not saying this is the best way, but this is in principle going to be not so bad. So f of 0 is just 0, f of 1 is just 1, and now we have a sum. I want to write this as fn plus 1 x to the n plus 1. And now, what is my range of summation for n? N goes from what to what? 1 to infinity. So before I summed from 2 to infinity, I had a subscript of n. I'm now summing from 1 to infinity. I have a subscript of n plus 1. Why am I doing this? Because I know fn plus 1 in terms of the previous. I'm going to get an expression for g in terms of itself. And we get g of x is x, plus now I have a sum, and it goes from 1 to infinity of fn x to the n plus fn minus 1, x to the n plus 1. And now we just have to be careful. So this is the same as x. Now over here I have fn. What power of x would I love to have? N. I have n plus 1, so what do I do? Erase the 1. Right. And then, I told you God had turned his or her back on us. God has come back and now sends lightning bolts. We are not allowed to just throw away the plus 1. So how do we do it correctly?
Or change the summation.
Well, we don't want to change the summation. Pull out an x. I don't want to rename it. I want to have fn x to the n. That's how my function g is defined. So all I have to do is I pull out an x. So it's going to be x, a sum, n goes from 1 to infinity of fn x to the n. For this one, I have fn minus 1 x to the n plus 1. What should I pull out?
Squared.
X squared. So I'll have plus an x squared, a sum, n goes from 1 to infinity of fn minus 1 xn minus 1. And now this is where, if you've taken a class in differential equations, or if you at some point in your life want to do this to yourself, half the time you just spend your life changing index of summation. So n goes from 1 to infinity of fn x to the n. Could I start my sum at 0? Can I just change the 1 to a 0?
Yeah.
Yes. Why? Because f of 0 is 0. I can make that start at 0 if I want to. Can I make this start at 0? No, because that would give me an f of -1. But notice, look, I have f index x to the same index. And since n runs from 1 to infinity, my indices run from 0 to infinity. So I can relabel all of this and have n go from 0 to infinity and do it as fn x to the n. I'm just changing my index of summation. If you look at what values it takes on, this takes on the same values as before. Okay? So this is just g of x. This is just g of x. That's just g of x. Okay, so we got g of x 3 times. And so this is the miracle. We now have a formula for g of x. We get g of x equals x plus x times g of x plus x squared times g of x. What would you like to do? Pull all the g of x's over. So you get 1 minus x squared times g of x is x. G of x is 1 over 1 minus x squared, or 1 over 1 minus x plus. Did I make a mistake?
You had 1 over something.
Oh, sorry, this should be an x. I'll write it better. Thank you.
Looks like a geometric series for some values of x.
So it's a geometric series. What's my radius?
X squared plus x less than 1.
X squared plus x less than 1. So I could expand this out with a geometric series. So this is what's technically known as a bad idea. It's a good thing to try. But if I try to expand this out in a geometric series, I get x times the sum, k goes from 0 to infinity, of x plus x squared to the k. And the problem is, I want to figure out what is fn. I want to write this as a sum of coefficients times x to the n. I want to pull off the nth term. And if I can pull off the nth term, I get the nth Fibonacci number. Well, the problem is x and x squared have different powers. So if I want to figure out all the terms that contribute to the 2014 term, this is a nightmare. There is a solution. It goes all the way back to something in Calc 1 that is usually, what was it, Calc 2? No, I guess it's Calc 2. I think it's the most hated technique in Calc 2.
Trig substitution.
Even worse than trig substitution.
Partial fractions.
Partial fractions, right? You know, I mean, I think if you make up a list of, which material did you hate the most in Calc 2, and you ask people, I think partial fractions is top of the list. No? Okay, so go learn partial fractions and realize how bad. No. So partial fractions, is not loved. And how many of you have seen partial fractions? How many of you have ever seen a reason why you would want to do partial fractions other than cookbook problems where you need to use partial fractions? Excellent. Where did you see partial fraction? It's going to be a long year, yes. So this is one example where we would use partial fractions. Before today, before preparations for this class, how many of you have ever seen a situation where you would want to use partial fractions? Or they've just been cookbook problems. Have you seen a situation? Where?
Stuff like this.
Stuff like this, okay. So this is one of the greatest examples of why we care about partial fractions. The difficulty here is that the x and the x squared are of different degrees, and that causes enormous trouble. So again, this is a really long digression to solve and find Binet's formula. The reason is, the purpose of this class is to use these riddles and problems as a springboard to good mathematics, and to try to give you a sense of how you should attack things. This is the most natural thing to do, to group it as x plus x squared. It's a geometric series. You know how to do geometric series. The problem with that is it's not nice. It doesn't expand well. So now we want to do partial fractions. So we want to write 1 minus x squared as 1 minus r1 of x, 1 minus r2 of x. And then we want to write x over 1 minus x squared as 1 minus r1 of x plus 1 minus r2 of x. The degree of this is 1 less than the degree of this. So I only get a constant up here. Okay. And so now what we do is we need to figure out what r1 and r2 are. And now, once we have these, we can do expansions. So for now, I'm going to hold off on figuring out what r1, r2, a, and b are. That's TlQ. That's a prerequisite for this class. I have never taught TlQ. I'm trying to go my entire professional career without ever teaching TlQ now because it's been so many decades. But I have been assured that you do partial fractions in TlQ. If not, some of them are easier. The r1 and r2 is not so bad to find. And once you know r1 and r2, now you cross multiply, you get systems of equations to solve. So I will assume you find them all. And so now let's assume we have g of x is the sum, n goes from 0 to infinity, of fn xn. And this is also the sum, I'm sorry, it's also a over 1 minus r1 of x plus b over 1 minus r2 of x. Now we apply the geometric series. And now it's going to be really nice because it's going to be linear in x. I'm not going to have to worry about problems coming from different degrees. And so this will give me a sum, k goes from 0 to infinity, of a r1, well, let's do the letter n, sorry, n r1 to the n, x to the n, plus b r2 to the n, x to the n. Well, I can pull out the x to the n. And what does that have to equal? It has to equal fn. So you have to do a little bit of work to then show that if you have these two power series that are equal, they have to be equal term by term. Anybody know how you would prove that they have to be equal term by term? Induction. Excellent. And by induction, what should you always guess in this class when you're in trouble? Induction. So first set x equal to 0, and then you get the 0th term has to equal the 0th term here. So now that you know the 0th terms are the same, subtract the 0 terms, divide by x, and then set x equal to 0 again. And just keep marching down the line like that. And there's Binet's formula. The nth Fibonacci number is a r1 to the n plus b r2 to the n. And now you just have to figure out what a, b, r1, and r2 are. Okay. I don't want to go through more algebra. This is more than enough algebra to do in public. But it gives you an idea of how you can tackle these problems. Okay? Yeah.
How did you get from the first step to the second?
From here to here? From here to here?
Yeah.
We just use the geometric series formula. So 1 over 1 minus r is 1 plus r squared plus r cubed, dot, dot, dot. And here, the first time I use r is r1x, and the second time I use r is r2x. And so I just expand each one of these. And so in order for this expansion to hold, r1 times x must be less than 1 in absolute value. r2 times x must be less than 1 in absolute value. So again, I strongly urge you to go through and calculate what is r1, r2, what are a and b. Okay. Any questions about this? So in the notes online, I talk about connections of this with probability. So generating functions occur all throughout mathematics. Probability is a wonderful place where the coefficients in your series expansion are often, the probabilities. What's the probability that the value is n? What's the probability the value is n plus 1, n plus 2? To me, I find this incredible. You start off by putting in these fn's, and you somehow use the recurrence relation you know to get something useful. At these group problems. And you're going from the lower left to the upper right, we will now allow to cross the diagonal, and we got a much harder recurrence relation to solve. And there, the recurrence relation involved a product, and of terms in the recurrence relation actually grew with n. So it's not fixed depth. These are much harder to deal with. It turns out the specific example I gave turns out to be very easy to deal with if you know something called convolutions. And so I thought I'd talk a little bit about convolutions today, and then I will have enough material on recurrence relations and generating functions. So, imagine f of x is the sum of an x to the n, and it goes from 0 to infinity. G of x is the sum, n goes from 0 to infinity of cn, cn, that would be stupid, bn x to the n. And we let h of x be f of x times g of x. It's going to be a sum, and m will go L, I guess. L goes from 0 to infinity, CL x to the L. Let's just pretend everything converges and we don't have to worry about justification. Does it make sense if you multiply the series for f times the series for g, you'll get some series for f times g? What is c of 0 going to be? So going to look at all the ways when I multiply this by this, I get something of x to the 0. So what will c0 be? It'll be not a1 times bn. I want c0. You're close. a0 times b0. Now, if I multiply these together, this is equal to a0 plus a1x plus a2x squared, yada, yada, yada. This is b0 plus b1x plus b2x squared plus yada, yada, yada. If I want to get a constant term, the only way to get a constant term is b0, a0 times b0. What if I want to get the linear term? What's the only way to get the linear term? Okay, what is it?
A1 is 0 and B0.
Right, I put here is a0 b1 plus a1 b0. It doesn't matter how you read it, I prefer to have my a's marching up and my b's marching down. What about c2? So a0 will be 2 plus a1 will be 1 plus a2 be 0. If I want to get an x squared term, I could have a constant term here and an x squared here. I could have two x's, or I could have an x squared and a constant. And so in general, we have a formula for the coefficient of CL. And so in this case, what we get is CL will be A0 BL plus A1 BL minus 1 plus AL B0. Okay, so if we do something like that, we now have a formula for CL. And this is just coming from multiplication. And then if x is sufficiently small, and that's going to depend on the coefficients, this will all converge, this will all be well defined, you'll have a new series. So we call this the convolution of the sequences A and B. And we often write C is A star B to denote convolution. So I'm not going to go through all the details, but why is this related to the Catalan numbers? So what is the recurrence for the Catalan numbers? It's something like Cn was, all the upper level minuses was like C0, Cn minus 1 plus C1, Cn minus 2, something like this. What does that look a lot like? Convolution of C with itself. Where is shifted by an index? So I'm not going to go through the algebraic details here, but basically you can now we'll do the same game we did for the Fibonacci numbers, and we can get a generating function for the Catalan numbers. And you get a closed form expression for the Catalan numbers. You can solve everything you want for them. It's wonderful. So I'm not going to go into details. I strongly urge you to try to do these calculations. But this idea of generating functions is extremely powerful. This is also used extensively in probability theory. Okay, any questions on what we've done up till now? So it's probably worth talking briefly about some very simple modifications of where the Catalan numbers came from. So we initially had them come from a line to walk in a square and a line to avoid a certain place. One, two, three. 1, 2, 3. This is a little extreme, but there's a massive flood, a gas leak, something has gone on, and this part of New York City is closed. Maybe there's a parade going on. Central Park. Right. Although actually if you walk in New York City, you might want to deliberately walk in Central Park, I'm not sure about. So these points are now unavailable. How many ways are there for you to get from here to here, again, never going above the main diagonal? How would you solve that? So this is a standard modification of what we've done. So what are your thoughts? So there's lots of ways we could attack this problem. Can someone really try to solve this problem? Count all of them. And if New York City is sufficiently large, which it is, that's not going to be pleasant. How could we go about trying to find how many ways there to get from here to there? What could we do?
Count the number of paths in that hatched region that follow all the rules that we want, and then that becomes a little difficult. That's not a great approach.
So something more clearly. So what do I want to do?
Well, it'd be nice if we could just sort of subtract off paths.
So we want to subtract off a certain set of bad paths. One possibility is you can look at all the bad paths. So maybe I still below all these points. That's going to become very hard. What if I look at all the paths that go through this point, all the paths that go through this point, all the paths that go through this point, all the paths that go through this point? Is that enough? No. Yes?
What were you talking about this way and this way?
Yes.
Or is that in this too?
Yes.
Okay.
Well, you want to go south or west. I mean, really.
What could be both ways?
Could be. Any Dr. Seuss fans? The Zacks? And the Prairie of Prax and north-going Sacs meant to south-going Sacs. And they had this huge fight because on the north-going Sacs I can only go north. I will try to find a Dr. Seuss story for additional comments. What else do we have to worry about?
Or I just have a different idea.
Okay. Well, if we first let's see what else we have to worry about. And what else do we have to worry about?
Well, all the other points.
Do we have to worry about these points up here? So one possibility is to find out how many ways can I get to all of these bad points and subtract. So that's one approach. What's the other? Did you have another approach?
Mm-hmm.
Okay.
So you look and you see that there's a bottleneck in the bottom right corner, and you could just look at the number of ways to get. There are 3 points. The very bottom left point. Yeah, that one.
This one right here? Over here?
Nope.
Here?
That one. Yep.
Okay.
Then
Okay.
there, and
Yes.
then go diagonal one, and then go diagonal one more.
To here?
Just look at, and then you can kind of split it up into two.
So you have to decide whether you want to go here or not. It's not.
The only points you can go through.
No, so maybe it's flat inside, but this point is accessible.
Get to there legally, and then how can you get from that?
Right. So for something like this, it's how many ways can we get to this point? And and for this particular problem, this is going to be much easier. So this comes down to the general principle of which do you want to count. And so here, it's much better to look for these 2 points than to say, how many paths do I have here, 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 and I have to really worry about double counting. Yes, comment? Okay. Other comments about this? So depending on how the problem is in terms of where things are, certain ways are better than others. This is taking up so much space, it's much better to come down here and look at just these 2 points. Is it really hard to figure out how many paths to get to here? No. To here? No. Yes?
Isn't there a possibility that some path could go through the dead zone and come back down and go through that point?
Well, so to get to these points?
Yeah.
No, because once you go through the dead zone, you're above them.
Okay. So, okay, you can't move down. You can only
Exactly. You're north going zacks. When dominating tracks in the periodic tracks, north going zacks meant a south going right. You can't go south. Now, when you look at this, if you try to go the other approach, you have to really worry about double counting. If I reach this point, it's possible I could reach this point as well. If I reach this point, I could also reach this point as well. There's all these different possibilities. It's a lot better to look at access points. Now, the problem is in general, the formula for this might be a little bit harder. Whether a valid path really going to exceed a certain amount. For this particular one, this is the way to do it. And so when we're doing these problems and competitions and whatnot, you always stop and look and see, is there an elegant solution? There has to be, or it's a bad problem, or there's a typo. And so there are frequently typos in the way problems are phrased. You might be subtly assuming something. You have a really way that will work, but it's computationally intense. Step back and try to think of another way to approach it. Okay? So the generating function approach allows us a way to avoid having to use divine inspiration. In a lot of these contests, it's timed. And so knowing the solution ahead of time helps you. Okay? I remember there was one time in high school, my school really didn't prepare for math competitions, but every now and then you look at a few previous exams before going to the contest. And I remember one morning I just happened to be looking at an exam and it was the exact same problem. They didn't change any of the numbers. And it's not going to look, you're just going to know you have the right answer. So I broke out laughing and I wrote 4 and spent absolutely no time on that problem because I just used the same numbers. You're not going to get that lucky on the Putnam or the green chicken or stuff like this. But there are so many standard problems that if you're looking at contests from all over the world, these problems are going to emerge again and again and again with tweaks. And so the Putnam or the green chicken could have something very similar to something we've seen before. The other thing again is I want you to see good mathematics. I want you to get a sense of if you continue to upper level math classes, what will you do? Why do you spend our time looking at stuff like this? What is it good for? And so again, the way we're going to work, the way you're going to get out of this class, I'm not going to force you to do any of this stuff. I'm going to put additional comments, so if you want to read further, if you want to see the connections, that's great. I'm happy to chat with you about it. This is supposed to be a pre-core 300 level course. The problems are not necessarily going to be easy, but the prerequisite material is going to be minimal. Next, in terms of topics, we need to do basic number theory, we need to do basic combinatorics. If anybody has any preferences for what we do next, send me an email in the near future. All right, so that's a colloquium today on continued fractions at 1. Hope to see you there.